Hey everyone. Now, I'm pretty sure many of you already know Mark, but for those who don't, and for those who can't get enough, let me tell you a little bit about Mark. Mark got his bachelor's in physics from University of New Hampshire, and swiftly accepted a research engineer position at the Magnetosphere-Ionosphere Research Lab there. After this, he went up to Dartmouth and did his PhD program, and then decided that it wasn't cold enough in New Hampshire. He moved on upwards to University of Calgary, where he was a postdoc. Following a stint there, he reversed trajectory, stopped back at Dartmouth for a short time, and then landed back at UNH, again in the Magnetosphere-Ionosphere Research Lab, this time as the head of the whole thing, and as a professor of physics for the Department of Physics and Space Science Center. And he studies experimental space plasmas with ground-based, satellite-based, and rocket-based instruments. In his free time, he likes to paddle and ponder about how great his grad students are. So.
Okay, when we get back to New Hampshire, we can talk about your stipend. Maybe I'll leave this here. Okay, well, good morning, everyone. It's very nice to have a chance to talk about Aurora. I can always talk about Aurora. I can't get my pen out of my pocket. I'll use the other one. Okay, green dot small. So I'm talking about Aurora and how it's coupled to the ionosphere, maybe a little bit. That's maybe less of a mystery or more well understood than its coupling to the thermosphere, which is actually has been studied for a very long time, and it takes place in many different ways. And that's what, so I'll go through, and I think maybe you'll be surprised at some of the stuff that's been done a long time ago. Before I really start going on about how this all happens, it's really important to understand that there really are very different kinds of aurora. So the way I sorted it out, this is my own text. If you're in a substorm expansion phase, so if you're at Poker Flat and you have nothing to do, so you take a flight up to Fairbanks and you want to see the aurora, you see a substorm expansion phase. In that case, the aurora really consists of two different types. There's two different types of aurora. You get the inverted V arcs that tend to be about 10 kilometers in north-south extent, and they go east-west over a very long extent. Energies are about 5 to 20 keV, isotropic electron distributions that light up that aurora. But at the same time, there's also alphanic aurora. The alphanic aurora is the aurora that you usually get right at the substorm onset, and then as this expansion phase moves poleward, the alphanic aurora seems to exist at the poleward edge of that. So the alphanic aurora is very different. It's about 100 or 200, just a couple hundred eV. And then the distributions there are not isotropic, but they're very much field-aligned. And if you look at them, they see these nice, tall, thin arcs. That's what you see in the substorm expansion phase. In the recovery phase, things are very different. That's where you see pulsating aurora. Pulsating aurora is typically 10 to several tens of keV in electrons. There have been reports of maybe even less than 10 keV, but typically it's 20, 30, 40, 50 keV, and I've seen up to 80 and maybe even 100 keV reported. It comes in pulsating patches. The patches are 50 kilometers, maybe 100 kilometers, maybe 200 kilometers in extent. Typical periods are about 8 to 20 seconds. And the patches can be very thin. So unlike the alphanic aurora that's real tall, or the inverted V that's also tall and extended, the pulsating aurora is very patchy. It's pancakes. It can be 5 kilometers thick, maybe a little bit more, generally not more than maybe 20 kilometers thick. And it's at lower altitudes because the more energetic electrons penetrate more deeply into the ionosphere and thermosphere. So the pulsating auroral patches tend to be about 95 kilometers, maybe even 85 or 80. On the day side, it's a different story again. There are poleward moving auroral forms, or PMAFs. The signature looks like alphanic aurora. It might be alphanic aurora. That's a good question. I have a movie of these poleward moving auroral forms, and you'll see that they're very thin, they're very wispy, they don't look all that impressive. It's not the sort of thing that you're going to buy a postcard for, I guess. And then there are traveling convection vortices that are sort of transient events, but there's aurora associated with that, and it's coupling to the thermosphere. So I'm really going to talk about sort of all this stuff, and it turns out this is sort of the order that I'll talk about it in, which kind of follows the chronological history of the work that's been done. Before I go, though, I want to talk about, I want to make sure that people understand a lot of what I want to talk about. The coupling to the thermosphere has to do with convection and joule heating, which is really driven by convection. So what does that mean? It means on the large scale, the convection cells that you might see in any textbook. So that's the big picture. But on smaller scales, associated with aurora, this is a cartoon from Jean-Marc Noël's paper from, when is this? This is quite a while ago, 2000. I just want to point to this and say, so if this is electrons precipitating down the field line and then lighting up the ionosphere here, of course the electrons come down, there's a current. The current has to close. If the electrons are coming down, the electric field is going straight up. If this electric field is going straight up here, this is the electric field plot, then you have to have electric fields pointing the converging potential pattern. So there are electric fields associated to result from the precipitation, from the current closure. All right? And that'll tend to give you these counter-streaming flows that we see a lot in this sort of stuff, and I'll show you examples of this. And so the point is, though, is that if you have these electric fields and you just do the right-hand rule, put your left hand behind your back, that's what. If you just do E cross B, then you get the counter-streaming flow. So if you're looking at the edge of an arc, for example, you have on one side you have the flow moving away from you, and on the other side it's moving towards you. And this is what you see a real lot. It's a standard signature of at least most of the aurora, not the pulsating aurora. That's a different sort of thing. These are more for the taller, thin arcs. Okay, so off we go into auroral history. When was the first connection made between the upper atmosphere and joule heating? The space race. The U.S. was launching satellites. Nobody really knew what to do as far as picking an altitude where you'd have a reasonable orbital lifetime. What they noticed fairly early on was that the acceleration of the satellites would depend on the solar activity. That didn't take very long at all. And how did they know about the acceleration of the satellites? They looked at it from the ground with these cameras. And you wonder about this camera? How big is this camera? That's a person right there. It's about the size of a person. 3.5 tons. These are big cameras. And I wish I knew where they were. I'd like to get one of these. They're such a cool camera. You can take a picture of anything. So this early discovery that the solar cycles or solar activity was connected to the satellite drag implied some kind of connection. And it didn't take long. 1964, Luigi Giacchia came up with the idea that it's joule heating. It's those increased solar activity drive joule heating, and the joule heating heats the upper thermosphere, so it just adiabatically expands and swells up and contributes to the satellite drag. So now going to this, making the connection to the substorm phases, that didn't take much longer. In the stuff that came on the previous slide, there was no connection to any particular type of aurora. It was just a general connection between solar activity and joule heating. But now we can talk about, so this is from a NASA technical report from 1971. The Air Force had developed the low GAX satellite, very low altitude. Maybe they didn't realize how low it was, but I mean, in the sense of drag. Perigee of 145 kilometers, apogee of 357. It had an onboard accelerometer, so it could tell when it was feeling satellite drag. Right? So this plot, I know you can't read this, I'll tell you what it is. This is the density of the atmosphere that it's flying through, the relative density. So this is the normalized to the background density of 1, and this is the increase, this is 1.3, so 30% increase in the density here when it's lined up with this is the magnetic latitude of the satellite. This is right at the auroral oval. So they noticed that basically when they were going through the perigee in the auroral oval, that the density was dramatically increased. So there's a connection there, obviously, to aurora. And this is sort of the first, as far as I can tell, this is the first report of the first connection of that. Okay. That's to do with the thermosphere expanding upwards. So that's one kind of coupling. But about the same time, his name is Charles Wilson. He goes by Bucky Wilson from Fairbanks. He's been active up until just a few years ago, actually. He was using ground-based infrasonic microphones to measure waves associated with aurora. So in other words, he had these microphones distributed around the poker flat, and he could detect aurora. What he called them, what he named it was auroral infrasonic bow waves. At first he didn't have the bow in there, but then he put it in, so it's AIW. But basically, if there's an arc, the idea is that if there's an arc moving in some direction, there will be a bow wave from that arc that you can detect on the ground. And it's just a pressure pulse that's going down. You require the supersonic movement because if it's not supersonic, you don't get the big pulse that comes with that. It's just it makes the signal too low in frequency to detect. Still, he made the connection to just electrodynamic drift and Joule heating. He didn't get into any of the precipitation stuff, but fell back to the Joule heating idea. He did continue more, and up until now up in 1972, saying that infrasound waves generated by supersonic auroral arcs are never observed propagating in a polar direction. The motion is invariably transverse to the auroral, let's just say auroral oval. And then even highly supersonic polar motions of arcs with strong electric jets don't produce infrasonic bow waves. So, and I have a note for myself here to explain, to make this point. The difference between the electric jet and current closure in arcs. When he was talking about looking at the effects in substorms, there's a cartoon in one of his papers where he takes Kasofu's picture of a cartoon of a substorm and he draws in the electric jet, which is completely valid. But then he's attributing that satellite drag to maybe the J cross B force from that electric jet, really to the electric jet. But it is true that in an expansion phase you have a lot of aurora and you do have that electric jet. But those are very different. The large-scale electric jet that can cover a couple hours of MLT, maybe something like that, that's quite a bit different than the current closure through the auroral arcs. And so I'm not sure that attributing, I think if the heating came really from the auroral arcs, and maybe it wasn't so directly connected to the large-scale electric jet, which is what he was trying to do. So this stuff sat for quite a long time, until recently. Victor Pascoe at Penn State picked up on what Bucky Wilson did a long time ago, and he modeled this. What you have along across the bottom, so he's got this basically a supersonic auroral arc coming from left to right. Across the bottom is the radial distance, that's 400, 800, 1200 kilometers, and this is altitude. So this is the I guess the current closure, moving from left to right. And it takes about 12 minutes before you get the first bump, and then there's a lot of this bouncing and bounces off the ground, back up to the upper thermosphere, and then back down, so you get a reflected signal. It's a much more detailed model than what Bucky Wilson had come up with, but it looks very believable. He's also Victor's done work on pulsating aurora too that I don't have here just because I have to draw the line someplace. On a different note, a connection to gravity waves, and I'm not an astronomer, so if I say something wrong, I won't be too far off, I guess. This is a paper from Oyama in 2001. I know it's hard to read this. I just copied this out of their paper. This is ISCAT data where they're looking at electric fields. So across the bottom, it's time. This is about 1, 2, 3, 4, 5 hours. So there is precipitation. There's an arc overhead, and that's what you see. This is this little spike here. This is what he refers to in the paper. He highlights this spike here, saying this is a perpendicular electric field. So this is convection here, and with that, this is ion temperatures. And you see the ion temperatures are bouncing around. So it seems like the ion temperatures are responding to that convection, and maybe this convection is drifting over the ISCAT radar. So you see these counter-streaming flows that I was talking about that you get with an arc. And what he did, you can use ISCAT indirectly to infer vertical winds, and these are this is the altitude and the motion of the vertical wind. So this is 150 kilometers, 200, 250s, and you can see this vertical wind. So this gravity wave is sort of breathing up and down in concert with the ion motion that seems to be driven, heated. It's Joule heating. If you have this perpendicular electric field, you have the Joule heating. So the Joule heating is heating the ions. And as it goes through these kind of streaming fields, I think this is what's going on. You see this gravity with the thermosphere just breathing up and down. There hasn't been a lot of this work on it.
What's the magnitude of the vertical neutral wind?
Oh, it's like 10 meters per second. It's very small. Okay, going to the night side now. This is pulsating aurora. And this is one of my favorite pictures, not because I'm a co-author, but one of my favorite pictures of pulsating aurora because this and a companion paper that was a statistical study of occurrence rates and durations of pulsating aurora, something that Sarah did, Sarah Jones. And with this paper, this is a movie, it's a good movie, you gotta see it. It's better than a book. It's like a 10-hour movie with no commercials and no breaks. But it's really a fascinating movie. This is near the end of the movie where you really see the dawn dust terminators just out of the field of view. But you will see pulsating aurora through all of North America. Everywhere there's a camera, you'll see pulsating aurora there, all the way through. Here, the pulsating aurora is very clearly, that's what this is here. These other things here, these are sites where it's probably cloudy and the street lights lighting up the bottom of the cloud, so that this is not aurora here, these bursts. In this movie, I think there are at least 3 times when you see a substorm. First, as the Earth is rotating, you see the substorm take off here, and this pulsating aurora going on while the substorm is taking place. When the substorm is done, there's more pulsating aurora, and then another substorm, and then another substorm, and it goes on and on and on. The point is that the spatial extent and the persistence of pulsating aurora is really very amazing to me. So this comes full circle back to Bucky Wilson, but now we're at 2005. This is from his infrasonic microphones again. What is on the bottom here, this is just the H component of the magnetic field, so this is just a substorm onset right here. Look at the top. This is time, so this is 5, 10, 15, 20 hours. So this is time of about maybe 10 hours, and these are signatures of the infrasonic signals. What he has here is what he calls the trace velocity. It's basically if you look at the arrival times of the different signals, and you say like if they're, and you just convert that to a speed. If the source is directly overhead, the speed difference would be 0. So if you have a trace velocity of near 0, then the signatures are directly overhead. And during this aurora, when we had all those pulses, during this event, when we had all those pulsating aurora, you see all these bursts of infrasound signatures with a very low trace velocity, meaning it's happening, coming right down from overhead. And if that's not convincing enough, this is a simple cross-correlation between the infrasonic signatures and pulsating aurora, and they're highly correlated at 0.08 Hz, which is about 12 seconds, a very typical pulsating aurora period. So the connection there is different. So this is not the bow wave that he was talking about when you had the motion of the supersonic motion of the arc. The idea is that the precipitation comes down. This is more energetic than the other precipitation. So this is coming down to maybe 90 kilometers. And as it reaches those altitudes, it heats up the ionosphere and the thermosphere and basically forms a region of heated populations that expands adiabatically. And as it does that, it sends a pulse down to the ground. That's what he thinks, that's what's in the paper, that's what the idea is. On a completely different note, NOx production. So this is related in principle, possibly, to the depletion of ozone. All right? Significant auroral precipitation may be a significant contributor to thermospheric NOx production, which can lead which leads to ozone. I didn't put that up there. I just told you. Okay. So the idea, pulsating aurora caused by 10 to 10 keV electron precipitation, frequent, widespread, long-lasting. And this should say it's not no produced. This is not a typo. It's NO or NOx is produced at such low altitudes it could potentially transport downward and interact with the stratospheric ozone. So what would be happening here, if this is a mechanism really for contributing to ozone depletion, is that the pulsating aurora, and keep in mind how widespread that was, because I've heard people say this idea doesn't have any real footing in the data, and I'd say that you got to see how widespread and persistent the pulsating aurora is before you answer that question. So the pulsating aurora electrons come down, and they're like 90 kilometers, and there's no doubt, and the Snowy experiment satellite observed this, NO production is increased. From there, it's just a question of whether you can take the NOx at 90 kilometers and mix it down to the lower altitudes, the 30 or 40 kilometers necessary to mix with the stratosphere. And the polar vortex that didn't just start happening last year, if you think it would, the way the news was going. Polar vortex has been there right along. But the idea is that the polar vortex comes along and interacts with these particles and just stirs everything up and does that mixing. That's the theory. It's really hard to prove, and it's not really proven. This is a figure from Isa Turunen, who's a big proponent of the idea. This is electron precipitation going from 120 kilometers down to low. This is sunrise. Just ignore this. That was the way his model ran. And this is the NO production And so here's the electron precipitation, 3 bursts, what did he say? 3 bursts of 5 K, this is 5 keV. The pulsating more energetic stuff is actually a lot more effective at producing NOx. But the point is that the model has a good connection between the electron precipitation and the NOx production. Okay, I'm now going to the day side, and I'm talking about traveling convection vortices. So this is a very different kind of aurora. This is on the cusp. This is a traveling convection vortex is quite a lot different than any other aurora we have. I was there for this event. This is in Svalbard. We were there to see about a rocket launch. This is what's called, and I'm not sure, I got to find out more about this myself. This is just soft electron precipitation, the so-called cusp precipitation, whatever that means. Sounds like just a fake made-up name. And you could see, we saw the sky light up with sort of this aurora turn on abruptly here. What's the time between 2-minute cadence between frames? So 2 minutes, 2 minutes, 2 minutes. The aurora turned on, then it got brighter, and then it expanded, and it started moving, and then it went forward, and it went right out of sight. At the time, we weren't sure what that was. We thought it was really cool. We weren't going to launch into it. We had no idea what it was. It turned out to be a traveling convection vortex. As it passed over ice cap, it passed right over the ice cap beam that was in the mode that was ideal for measuring this sort of stuff. It's a kind of a funky, if you're used to looking at ice cap data, it's kind of funky. And so if you're not used to looking at ice cap data, I'll explain what it is. The top panel is electron density that would be affected by precipitation. The second panel down is electron temperature. So you see some precipitation is lighting up at a higher altitude, so 200 kilometers. So this is the softer precipitation. But something is heating this electron population up earlier. And then this convection here lights up the ion. This is ion temperature. So there's convection. So there's Joule heating here that's heating up the ion temperatures. This would be related to ion outflow. Let's just skip that for now. So the point is that in a traveling convection vortex, you have both precipitation that comes down in a fairly localized area, but there's also an ionospheric convection. The convection in that case it's a tornado. I mean it's a vortical convection, and as it goes over the magnetometers, because the precipitation carries the currents. This is a very classic traveling convection vortex. It's just this bipolar spike, bing, bing, bing. This is Nealison, about 100 kilometers to us. This is where we were in Longyearbyen, so it was directly overhead. And you see it, that's clear signature. You can, if you make some bold assumptions maybe, you can infer the convection from the magnetometer signal. You need to assume the right conductivity and so on. And you can see the vortical motion right in there, right from the magnetometer data. This plot, I know it's hard to see. This is from Anasuya Willia. This is from her Fabric Pro, Imaging Fabric Pro. So this is looking at the Fabric Pro, and this is 6,300. So this is looking at the 250 kilometers or so. Looking at the traveling convection vortex. Ignore this part. This is earlier on. I'm not sure what this is about. So these are about 7 minutes between frames. Before the TCV started, things are pretty smooth. And then the TCV came on, and then all of a sudden you get some divergence down here. This is the southern end of the field of view. So we see some divergence down here. It's not a great measurement, but it's enough to say that yes, the thermosphere is definitely changing, is responding to the TCV. No surprise, I mean, you get into convection, so you'd expect that to happen. Okay, a lot of what I've been talking about has been done before, has been done quite a while ago, and you know, the scientific interest changes a lot with, depending on what you're talking about. I would say probably the most attention-getting topic these days related to ionosphere coupling has to do with these speed bumps. This is a well-known plot at this point. This is from Herman Moore's 2004 paper where the CHAMP satellite flew multiple orbits. Each one of these, so this is time. This is starting at 1, going to, this is about 13, 14 hours worth of data. So these are multiple orbits. CHAMP is about 450 kilometers. This, along the vertical axis, is, again, data from an accelerometer on the satellite. So you're seeing a really good measure of satellite drag. This is obviously a lot better quality than what the Air Force did back in 1971 or something like that. you're seeing the satellite drag. So each sort of sine wave is one lap around the Earth. So that's one orbital period. Orbital period, orbital period. But then what I want you to look at are these bumps. These are not arrows drawn. The timestamps are right near this. It might look like an arrow. This is not an arrow. This is the speed bump. This is really measured by the accelerometer. These are the northern hemisphere ones, and these are the southern hemisphere ones. And they're very common, and the density enhancement can be almost a factor of 2. At least a 50% increase is common, and the average is 1.33 or something like that. So that's really neat. And actually this paper, or maybe this plot, is something that Herman Lohr showed me before the paper came out a long time ago. And as soon as I saw this, I said, well, that's pretty neat, because that must be, the electron precipitation in the cusp must be what's doing this. And that was the beginning of a long battle, because I got told by many people, no, it's Joule heating, it's Joule heating, it's Joule heating, it's Joule heating. But now I think we know better. The electrons do have something to do with that. So Herman's paper was followed up with 2 sort of statistical studies. One, just a very general statistical study. The mean amplitude of the prominent relative density enhancement peak shows no seasonal variation and amounts to enhancements of about 1.3. I'm surprised that there are no seasonal variations, and actually I'm not sure that this is consistent with other stuff. There's a linear relationship between VZ. VZ is the ion outflow, and electron temperature with only a slight variation from season to season. That's sort of the background information. Field line currents tend to increase in the summer. I'll show you another plot in a few minutes where these speed bumps are very highly correlated with small-scale field line currents, which mean auroral precipitation. Stephanie Rentz was his grad student, and she had another paper, earlier one following 2008, and she made the point that the signatures are stronger in the northern hemisphere, and the solar zenith angle appears to play only a minor role. So signatures are stronger in the northern hemisphere, and there's no seasonal variations. It sounds like a contradiction to me, but maybe I'm just misunderstanding something. From her paper, I copied this plot. This is observations of a big statistical study, I think over 4 years. The northern hemisphere and the southern hemisphere. This is March, June, September, December. So you really do see in the northern hemisphere no significant seasonal variation at all. But you definitely see more. These are not densities. They had a criteria for saying this is for counting bumps, basically. So this is the number of bumps in the location. So you definitely see more in the northern hemisphere, depending on the season. So the southern hemisphere, this is March, this is September. So the southern hemisphere is kind of light at this point, and you're not seeing much, which is no surprise. Interesting stuff. Okay, I want to go back and point to this plot that was in Herman's original paper. I think it was where he sent it to us. One or the other, there it is. This is the accelerometer data. This is going from degrees in latitude, 55, 60, 65, 70, so it's going forward. This is one of the speed bumps. I guess these are too. I'm not so sure about that. We're focused more on this. And the point that he made that's been absolutely consistent is the connection between the speed bumps and this is magnetometer data, each component of the magnetometer data. So if you're flying a magnetometer through a current sheet, you remember from Griffiths, right? There's a current sheet, so the magnetic field is going to be sort of parallel or tangential to the surface of the current sheet, and then reverse on the opposite side of the current sheet. So as the satellite approaches the current sheet, you'll see the magnetic field get stronger in one direction and then flip. So this looks just like it's going through a current sheet right in the vicinity of where the speed bump is. Right? So the connection to the currents, the field line currents and these speed bumps is very strong. And field line currents can only be electrons. Electrons going up, whether they're going up or down, it doesn't really matter, because the current closure is going to say if they're going up here, very nearby, they're going to be going down and causing the aurora. This is a sort of one result from modeling from the Marsden chunk. You're just using model results to try to replicate what was done with CHAMP. They were trying to look at enhancements by a factor of 1.8, which is on the high side for sure, at 400 kilometers altitude. But the point is that the heating needed to be increased by a factor of 110 over the background. So the ion temperatures would be, instead of 1,000 Kelvin, would be up to 10,000 Kelvin, which is not, so it just doesn't happen. So the point is that this is not the solution. You can't just crank the convection through more. This is an observation from Jim Clemens using the Streak satellite. Streak satellite was fixed at 250 kilometers. This is a funky plot to look at first. It's kind of bewildering, but this is magnetic local time here. So this is this is magnetic local time. Along the vertical axis is the magnetic latitude. So up near the polar region, near the cusp region, where you're near 90 degrees and minus 90 degrees of the southern hemisphere, you see more blue. The blue has to do with the pressure difference from the nominal background. So it's blue, so it means the pressure is lower. So it means the density at 250 kilometers, from what they can tell, the density is actually depleted, not increased. And so the conclusion from this that they make is that if it's Joule heating, sort of traditional Joule heating down near the E region, that should mean that you have sort of monotonically decreasing densities as you go up in altitude. But this says no, there's sort of a depletion in density at lower altitudes. Probably what's happening is that the whole process of the thermospheric upwelling is taking place above that and sucking the density up above it. So that's their conclusion. All right, I'm about to go sort of shift gears a little bit. This is sort of a random spot to put this, but I want to make the point that because of sort of stratification maybe in the thermosphere, this is sort of how things look. You have nitrogen, and this doesn't, there's absolutely no sharp line, but nitrogen is sort of predominant, going up to about 150, 160 kilometers, and then it's molecular oxygen up until about 1,000 kilometers. So the idea is that this thermospheric upwelling is neutral atomic oxygen. That's the conclusion that it seems to be holding up. Okay? So the story we end up with is this. This is sort of, obviously it's just a cartoon, but trying to put in one place, these are the options we have for producing these bumps. Here's one of the Champ bumps from the previous slide. This is what it looks like. And so somehow Champ is flying through and seeing this bump. It can be driven by Joule heating, just the classic Joule heating that I've been talking about right along. Or, there's these connections with strong field line currents implies that particle precipitation, maybe waves associated with that particle precipitation, and maybe it's the Joule heating associated with the wave, that may play a role too. Okay, with that idea in mind, it's time to talk about a rocket. We just had a rocket launch in December that was targeted at making all these measurements to try to answer this question. To give you some background on where we are 15 minutes left. That's where we are. Okay. This is launched in Norway. This is the Andøya Space Center in Anden, Norway, and this is, you are here, we were here. This is in Longyearbyen, where the ISCAT radar facility is, and we had the ISCAT radar beam looking straight up the big dish, the 42-meter dish, looks up the local magnetic field line to give us all the ISCAT data that we need associated with any event. The idea, this cartoon was drawn before launch, and it didn't change after launch except at the altitude. We used the actual altitude instead of the predicted altitude. This PMAF is what we expected to launch into. The PMAF is the forward moving roll form that I talked about, and that is probably the kind of aurora that I can't imagine. It's the most common aurora by far in the cusp, and if Champ is seeing these speed bumps, it's got to be associated with these PMAFs, which absolutely are, a kilometer scale, very thin, very small scale, and have strong field line currents, strong electron precipitation. I got to throw out a tip of the hat to the NASA Wallops people, to the rocket program. They're always doing really good stuff, but one thing they did this time, because we knew that we were going to be going on the up leg, our prime time was going to be coming through apogee and then down on the down leg, where we kind of wanted to come along the same region where the ISCAT beam was, and the all-sky cameras, and a whole ton of equipment on the ground. Ground-based observations were beneath this, so this is what we expected to fly into. What that meant was that we always configure the rocket so that we want the spin axis, not always, but in this case we wanted the spin axis parallel to the background field without the attitude control system blowing gas all over the place, because as soon as we do that, we can't measure electrons and ions, and neutral particles as well. So what they did here was this so-called predictive alignment maneuver. The rocket on the up leg has a GPS. The GPS figures out where the rocket is. The GPS is real smart. The rocket is real smart. It takes that position, it projects the orbital trajectory to t plus 550 seconds, so that's about right about here. And then it uses that location, plugs that location into an onboard IGRF model, and says, okay, so the orientation is going to be this way. So it does the maneuver here, so that it goes up like this, it does the maneuver here, so that it comes down and just follows along the field line without any further ACS maneuvers. And it got within 1.5 degrees of the background field, which is great for us. Okay, I'm going to talk about more of the observations and talk more about sort of the competing theories for what's driving the upwelling. But in order to do that, I have to explain a little bit. Most of this stuff, some of this stuff has to do with ion outflow, and that's part of the story. So, relevant process that we need to talk about. Joule heating heats the thermosphere at altitudes near 100 kilometers and causes neutral upwelling. That we know is true. That goes back to the 50s. The Joule heating also heats the ionosphere in this region, and likewise causes it to expand vertically. This is one of two mechanisms that contribute to lower altitude stages of ion upflow, type 1 ion upflow. If the consensus or the feeling these days is that ion outflow is a two-step process. The lower altitude from 0 to maybe 500 kilometers, not 0, a couple hundred to about 500 kilometers is the ion upflow. So that brings those oxygen ions up to 500 kilometers. That can happen one of two ways. It can happen with Joule heating, and we see that, IceCat sees that all the time. That TCV, that traveling convection vortex, that was part of that story. That's the type 1 heating. The other way to do it is with soft electron precipitation. With soft electron precipitation, the electrons come down, they're like 100 eV electrons. They deposit their energy at altitudes of around 250 kilometers. They heat the cold background electrons, and so that whole volume of heated electrons expands adiabatically upward along the field lines because it's tied to B. And as it does that, it lifts the ions up with it. So that's a completely different mechanism, one more that's more sort of vertically structured, and that drives the first part of the ion upflow. For it to be outflow, there's the second part that involves probably interactions with waves. We're not doing that here, but just so you know the story. And that's what I said there. All right, so we're talking about, there's a distinction, important distinction that should be made between ion upflow and ion outflow. Outflow means bye-bye, it's gone. Outflow means it's coming back down, maybe. Because if you move out of the heating region, if the Joule heating or the electron precipitation stops, all of those ions will come back down. You do get downflow. Okay, so for the small-scale neutral upwelling, the speed bumps, here are 4 recent papers, sort of competing theories, if you will. Jeff Crowley had a paper a few years ago. Wow, 2010, it seems so recent to me. Okay, anyway. The idea that Jeff, and this is not fair to Jeff, because if he's not here, he would be saying that precipitation has something to do with this. But it may be, I don't know how the details of the model. He uses AMI and high-GCM. So the precipitation controls electric fields and controls Joule heating. But he's on the Joule heating bandwagon, absolutely. Large scale and small scale, and he'd make the point that the small scale stuff is very important. Antonius Otto had a model that is actually, Brent Sadler used the model to publish a paper in 2004, but Antonius' model was actually what Herman Lohr referred to in the 2004 paper. This is a very different type of process. This goes back to the ion outflow that I just explained, and it has to do with the process that drives the ion outflow drags up the neutrals as well. So you turn on whatever mechanism you turn on, so the precipitation can drive the ion upflow, that can bring the neutrals up with it. And then that's one way to bring the neutrals up. Ben Zhang has a different idea, that the soft electron precipitation enhances the conductivities in the F region, so 250 kilometers, and that intensifies the Joule heating at those altitudes. So this actually is consistent with the streak observations of Jim Clemens, where he said the heating process must be occurring at higher altitudes. So this works for that. And then Doug Brinkman, working with Jim Clemens, has a similar model, except theirs also takes into account a contribution from the direct heating of the electrons to the neutrals, which takes a couple hours to do, but in reality, that's how long it takes. Okay, there's our rocket. I've got to show you the picture of the rocket. It was a big rocket, 70 feet long. Yes, no MKS units here, I know. 70 feet, over 11,000 pounds. This was done by Shane Thompson, who's the mechanical engineer. This is him right here. So it was a very big rocket. But we're pretty thrilled with the whole thing. I'm just going to fly through here. This is a list of all the instruments. There were 13 different instruments on the rocket, and everything worked. This is the ensemble of slaves that I had last summer. Some of them are still here. I'm going to have to move real fast because I have like 7 minutes left. We had ideal solar wind conditions. The day that we launched was, it was real a nail-biter sort of launch process. The day that we finally launched, we looked at the solar wind, and this means like I get up at 2 o'clock in the morning because that's when we're launching. We got to be ready to go by before noon. We had the right solar wind. We had BZ being -2 or 3. We had a strong BY. The BZ being -2 or 3 means, according to Chelmar Aksavik, the local expert, he said, when the BZ is -2 or 3, that's when the cusp is right overhead. And he's exactly right. And he looked at positive BY. So the cusp is going to be before noon, so we're going to be ready to go early. And we had good solar wind speeds and good densities, and everything was good except that it was snowing. Snowing in Solid. This is cutlass data, and I'm just showing this real quickly so we have cutlass data. This shows I'm just going to fly through this. This shows the Okay, I don't want to pay any fines or anything. All right, so this comes from Tim Yeoman. He was working very closely with us. It's greatly appreciate his help. It's super darn, so they weren't getting scatters initially, and then when we started getting into the cusp, and at this point I think we had actually called for the launch, but we had other signs that were in the cusp. The sign being Chelmar was telling me we're in the cusp, and I'm like, okay. So we have, as soon as we started getting signatures, we see the yellow means velocity away from the Finland ground station. So there's the Superdar radar there, so we had poleward moving flows, the sign of confirmation that we're in the cusp. So we have really nice data there. ISCAT data, again, so this is electron density, electron temperature, ion temperature, and ion velocity up the field line. These are Chelmar's notes here, but basically the red line is where we launched. It's hard to see a little bit. You can see that the electron temperatures, we were getting lit up, getting heated, bursts of electron heating as each forward moving roll form passed over, and I'll show you that. It's a short movie to show. So you can see these heated electron populations, and this is what drives that type 2 ion outflow. These heated electron populations expand and pull the neutrals, pull the ions up with it, and maybe pull the neutrals up. We had a real lot of ground support. This is from Joran Moens and Lassie Clausen, who's working with them. Their all-sky camera, very super excellent camera. Ignore this fuzzy stuff at the beginning. These are kilograms, so this is this is 5577. This is 6300. I'm quite sure I have the order right. It doesn't make a big difference. You see, we can see both. So this is 7:13. We launched at 7:34. So this is about 8 minutes after launch. This dotted line was the nominal launch. We always put that on the screen so that we can see if there's aurora. We don't have to say, do you think we're going to hit it? Do you think we can hit it? We have good belief that we're going to hit it. This was from the kilogram that again comes from the all-sky camera with notes that I have from my notebook and from some of the Skype chat that we had. So it was snowing, less snow, we could see stars, and then Chelmar said we're inside the cusp, and in the meantime we're talking with the people down at the rocket range in Andoya. And take the clock to T-minus 15 minutes. That's here. We had seen the right solar wind conditions, so we weren't surprised to see this, what looked like a forward moving auroral form. So we started getting right to the edge of our seats here. And then dropped from T-minus 15. We saw the second PMAP going. We said drop from T-minus 15 to T-minus 2. And we saw the third PMAP going. And then we finally said, like, okay, let's go. We were expecting there will be another one. And we launched, this is a dash line here, we launched, and we hit this guy, which is expanded here. And if you can see this line, we went right smack through the middle of it. So as I tell some people, if I was ever going to put this in a proposal, say we're going to do this, the proposal would never be. And it shouldn't be. But we nailed it. We had a lot of luck. Speaking of these PMAPs, I think one of the really neat things, Fred Singerness is at UNIS. He's he has several different kinds of cameras, and he's always playing with the cameras. And so we had Joran Moen's all-sky cameras that are really highly calibrated. This is a Sony camera. It was just an uncalibrated sort of pedestrian camera, not a low-light camera. I don't know. Keep going. Oh, there we go. Okay. All right, so I copied down, so this is one of the PMAPs. And the point that I want to make is that when you look at these MSPs, or these keyograms, it looks like one arc moving forward. But when you look at the high resolution data, like it's not a single like broad 10 or 20 kilometer wide arc. It's full of these very thin wispy arcs. And that's exactly what we got with the electron instrument on the payload. But that's what happens. Every about 15 minutes or so, the arcs appear on the southern end, and then just this collection of thin wispy arcs moves ahead. Right now, that's, you can't read, I don't know if you can read this. This is 723. I'll let it run just for a minute, so you can see what we launched into. 723. 723. The local people were helping us out by clearing the ice off the dome, which they did by using what was the vodka they used? Vodka that had an excess of a certain kind of vodka. Seriously, and that's what really got the ice off the dome. So we had just launched now, so we're on our way up that long. Get my hand out of the way. We were up on that long trajectory, and here comes the arc that we hit, the one that we went through. And this is, like I say, it's not a single broad arc, but it's very dynamic, and it consists of very thin, wispy arcs. You can see the reddish color, that's 630 nanometers associated with that soft electron precipitation. Okay. This is what we've been using just to sort of tell the story about the launch. This is the electron data. This is energy from 0. It's actually to about 15 keV. This is time after launch. And people say, why don't you use UT? Why don't you use UT? There's a good reason for that. And that's in the whole payload assembly and buildup. We refer to T plus from, when the launch takes place. Everything is referenced to that. This time is, every event is time. So we'll get UT on it. We know what the UT is. We launched right at 7:34, so we add the seconds if you want. So on the up leg, you can see the isotropic plasma sheet stuff, very clear, about 2 keV, very typical stuff. I don't really understand the 10 keV stuff, but there it is. And then as soon as we hit the cusp, things change. We see this is like 15 eV, so we see some very soft electron precipitation there, very narrow, very confined. And then as we go a little bit further forward, bing, 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 a bunch of these arcs. And if you look at them in detail, and we have about, I think it's 40 measurements, 40 pitch angle distributions per second. We have a lot of, we have like over 3,000, almost 4,000 pitch angle distributions. So given the time is really tight, I'm going to just kind of skip over stuff. We have ions. We have ions from Jim Clemens' ion spectrometer. We have electric fields. This is, a lot of this data is preliminary. We launched in December. We're doing the best that we can to kind of keep up with the data. This is, I just copied the electron precipitation data from the previous slides. This is the electric field data from Dave Heisel at Cornell. And basically what you see is that the convection, the counter-streaming flows that we see with these arcs is not very impressive. It's 100 or 200 meters per second. It's pretty slow. It's just not, these flow channels associated with these arcs are surprisingly low in speed, so they maybe don't contribute so much to the thermospheric alcohol. A couple of really impressive new observations. This is from Jim Heck's set of photometers, a photomultiplier tube, looking up above the payload, but he'd have to explain this. These wiggly lines are N2+, that's the bottom line, but I mean, it's after a lot of processing and subtracting model results. I'm sure he's probably talking with those CDAR people and showing the same result with more information than what I have here. But it's a definite signature of N2+ above the payload. So we're 350 kilometers, at least 300 kilometers, and we see the N2+, which is very cool. This is what's called sunlit aurora, which has been seen before. It's been seen from the ground by Carl Stormer. I have that book, and you can see he talks about this blue aurora is 4278, so that's N2+, but it's up to 1,000 kilometers in altitude. It's excited by solar UV. What the N2+ ions are doing up there, we have no idea, but maybe we have the data now to figure that out. The SME imager also had a couple papers on the sunlit aurora, and then the MSX satellite had sunlit aurora. So we have N2 plus observations along with a whole suite of other observations that go with it. This is Jim Clemens' ion gauge instrument. Basically, he's still working on that. We had another observation that I'm very happy with that came from a suggestion by Dirk Lumerzine, probably from a GEM meeting a long time ago, where I told him we were doing this rocket. And he said, you know, if you're looking for atomic oxygen above the payload, you can think about putting a photomultiplier tube and seeing if this UV from the sun would give you a signal with just, you know, a resonant excitation. And I said, oh, that's a good idea. Let's try that. In the rocket program, you can do that. You can say, like, we want to add an instrument as long as it draws no power and it's massless. You can do that. So, so the usual constraints. So going on the up leg, you can see we're just the instrument is turned on here, but we're just down in the signal to noise. We don't really get a signal. This is an extremely simple instrument, not cool. You know, like it was very seat of the pants. But then when we start getting into where we have the aurora overhead, we see this big, broad, we see two things here. We see the big, broad bump that is exactly the same size as the Champ bumps. I believe that this is one of the Champ bumps observed by the payload. And we see some structure, and this is probably driven by precipitation. So there's two things going on. I'm going to skip that. I'm going to skip that. This is part of Antonius's model. So one science point, one idea, one important point we need to take into account. This is time along the axis. This is luminosity. This is at the foot point of where the rocket was at t plus 600 seconds. So a fixed point relative to the ground. These are the PMAFs moving overhead. Let's say this is a 6300. So we had one PMAF fly over, then another, and then the fourth one that we launched into. And my point is that the heating is not the heating. It takes a long time. It takes a long time to put heat into those neutrals and to get them to come up. We waited intentionally, and we had, this is all part of the plan, we waited for these PMAFs to go, we waited for the heating to take place. We hit the fourth one, and so what does that do? So we ran Antonius's model. Brent Sadler works with me, ran Antonius's model, and he turned on precipitation. This is just a short model, so it's some funky time. On and off pulses, 66 seconds, on, off, to emulate the passage of these polar roll forms, these thin arcs. And here you see the electron temperature spikes, this responds right away to the precipitation, bing, 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 bing. The ion upflow responds with decreasing interest as it goes on. I don't understand that. But then the neutrals, you see the relative density. This is just a quick model, so this is not at all a good scale. But the density takes a long time. This is almost 7 minutes before we get up to here, and it's nonlinear. So the point just is, so when you look at this, you got to take time into account. And there's the conclusions.
Are there any suggestions as to why the speed bumps are different in the northern and southern hemisphere Champ? And I just would mention that first slide that you showed of the speed bumps was at equinox, so it can't be a seasonal effect. It really does have to be a hemispheric effect.
Their idea, I meant to say this, they say in their paper that it's not a sunlight, and I'm not sure how the sunlight cannot be playing a role here, but that's a different point. But the idea is that the dipole field, the dipole axis and Earth's spin axis are not only oriented differently, but there's an offset. So there's a difference there. And I read the paper, and I've read that statement a few times in this paper, but they're attributing it to that offset. Maybe not any kind of level of detail. So I'm not sure about that. It's a more of an open question.
Okay, I don't know whether you can find it, but there was a slide where you showed a speed bump kind of enlarged, and there was a scale underneath what the latitude.
Like one of the very first ones?
One of the first ones. And it was just one speed bump when you saw it.
Yes, it was latitude.
Okay, my problem with that was that if that is really true, then that speed bump is not well tested. Whether it's kinetic or geographic, that latitude is not.
Well, this was one event. I mean, things. So, if you go to also this statistical study, you see that these speed bumps are distributed all over the place. So the fact that they seem to be tied to the PMAS, I think, is significant, but that may not be the only mechanism that's driving them. So maybe it's not exactly the cusp. And then obviously there are a lot of events here that are outside the cusp. So, I mean, so it's maybe dual heating near the cusp or
But
other
you know,
type of-
there is another overall much lower latitude, which is really inside the magnetosphere, the type of energetic particles coming in. And it's much more likely to get dual heating there than at the cusp where everything stops at 200 kilometers. But you probably will do this.
There's another question over here.
Okay. Talk to you more, Steve. Yeah.
You know, you talk about dual heating, and that's all fine that it's heating in the lower ionosphere and everything, but as far as the response of neutrals is concerned, what matters more is the dual heating bringing in mass. So if you're going to have a high altitude ion density, you know, higher than usual, like in the cusp, you're going to have electric fields. It's going to be a lot easier to lift the neutrals because you have large neutrals to lift. The other thing is the temperature tends to be constant, so you tend to convert your energy into potential energy by lifting the neutrals. I'm not sure how the numbers line up. I've tried it. I think it's something we should beware of. Dual heating is fine. It dumps energy where you say it does. But the impact of the neutral motion is really very massive. If you're higher up, you can deposit dual heating higher up here to change.
Well, I mean, two of the models are assuming, making that assumption that the dual heating is taking place at like 250 kilometers, right? So the Doug Brickman model and Ben Zhang's model, they both have the dual heating taking place at higher altitudes exactly for that reason.
Eric.
So Deng et al. Did a paper which used the model to look at the combination of dual heating and low energy auroral precipitation. And she showed that as the energy of the low energy precipitation decreases, then the dual heating goes up in altitude, just like you're saying, and then the reaction is amplified greatly. And so she does exactly what you're talking about.
Yeah, I know that paper just came out. There's been a couple of papers that don't have it. Okay, all right. I can. There's a lot going on these days with this topic, I have to say. I'm surprised how many posters are out there. Yeah, one of the questions about that, I mean, that's just to do with the precipitation. It has nothing to do with any sort of electrodynamic process where the electrons come down and can do like, you know, the type 2 ion outflow sort of thing that may or may not have.
Last question?